Good morning, everyone. Good morning, everyone. This is day two of the Harmattan School for Medical Physics. My name is Chidima Maduka, and I am most delighted to be your moderator for today. And co-moderating with me is Favor Alioke. And we're just here to ensure that you have a smooth learning process. So if you joined yesterday and you've joined in this morning, please kindly send in your name in the chat box, your name and where you're joining us from, as well as your institution, so we can also connect with each other in the chat box. And if you were here yesterday, we also like to get some feedback. Tell us one thing that stood out for you in yesterday's session. So without further ado, I'm going to be handing over to Favor as she introduces our speaker for today. Thank you.
Thank you so much, Chidima. Good morning, everybody. Good morning, Dr. Iyobosa. Good morning, Mr. Victor. Welcome to our guest. And I'll just go right ahead and introduce our guest for today. While I do that, please, I want to encourage everyone, just as Moderator Chidima had said, let's do well to send in our names, where we're joining in from, and also what stood out for you in yesterday's session. You can even go further to share what you're expecting to gain from today's session. I'm going to be introducing our guest, Dr. Kumar. Dr. Kumar, you're going to forgive me by pronouncing your surname after introduce you because I don't want to mispronounce the name. So Dr. Kumar works at Guy's and St. Thomas NHS Foundation Trust in the Physics and Clinical Engineering, London, UK. He has worked on multidisciplinary research studies to help advance the use of diagnostic and therapeutic ultrasound and authored approximately 100 scientific publications. Wow. With a commitment to clinical service and education, Dr. Kumar lectures at King's College London and is the physics module lead for the MSc in Medical Ultrasound at Imperial College London. So the Harmattan School of Medical Physics is excited to have Dr. Kumar this morning, and he will be taking us on. We have two lectures, but the first lecture which will be taking us on is how sound waves interact with the body, and this is going to be a 45-minute teaching session, after which we would have a 10-minute question and answers. So over to you, Dr. Kumar. Welcome.
Hello, everyone. Thank you for this introduction, and thanks for inviting me to give these talks on ultrasound. So I'm sharing my screen, and let me know if you can see the first slide with the Mentimeter code.
Yes, we can.
Great. So if I could ask participants to take this code, log into Mentimeter, and as I'm giving the lecture, you can add some of the key words on how ultrasound interacts with tissue and artifacts that I'm talking about. So it's just a little bit of an participation that you can do, and it will produce a nice word cloud at the end. So if you can scan the code, or maybe if somebody could put it in the chat as well, or should I put it on the chat? Okay. I'll come back to the code later as well. So what I'm going to talk about is some of the topics. What is ultrasound? Why is ultrasound important, especially medical ultrasound for diagnostics and for therapy? A brief history of ultrasound, and then the key physics aspects. How does ultrasound interact with tissue? How do ultrasound transducers work, and basic scanner operation? And then from the understanding of the physics of interaction of ultrasound through tissue, hopefully you'll be able to interpret and appreciate different ultrasound imaging artifacts, because imaging artifacts are quite common. Grayscale imaging has a lot of artifacts, and you need to be able to understand the physics of how the ultrasound is propagating in order to appreciate some of these artifacts. So that's the outline of this first talk. So you probably appreciate there are two main types of waves. Ultrasound is a wave, it's a high frequency wave. In fact, it's a high frequency sound wave. Sound wave is a mechanical wave. It requires a medium through which to propagate. If there's no medium in a vacuum, there'll be no sound that can propagate. So the medium is reacting to the pressure pulse, and the wave is oscillating, the particles oscillating around the center, and this is pushing the wave to travel from one place to the other without any bulk motion of the individual particles. So energy is transported from one place to another. And ultrasound is a longitudinal wave, so the particle motion, the red dots, particle motion is in the same direction as the wave is traveling, as opposed to longitudinal waves, I mean, that's transverse waves, sorry, in which the particle motion, the wave below, is perpendicular to the wave direction. So ultrasound is a longitudinal wave. It's a high frequency wave above the hair ring, so above 20 kilohertz. That's the frequency at which ultrasound is defined. Ultrasound is important diagnostically. In the UK, specifically in England, the last year, they had over 11 million diagnostic ultrasound scans. And ultrasound is second only to X-ray in terms of the number of diagnostic scans that have been performed. So ultrasound has a lot of attractions. It's cheap, it's convenient. Almost anyone can pick it up and start to use it, which creates its own problems in terms of training and governance of the use of ultrasound in hospitals. Because it is so straightforward, you can even have portable ultrasound devices that clinicians or anyone can use. So it's increasing in its prevalence. The one on the left is showing a kidney, a B-mode grayscale image, and on the right we can see a use of Doppler to look at blood flow. And these are two particular ultrasound modalities that are used in the clinic. So you might or might not recognize this ship. It's the Titanic. What has this got to do with the ultrasound, you might wonder? So the sinking of the Titanic in 1912 really inspired people to look at ways of detecting obstacles, icebergs, or even other ships using sonar. So this was an inspiration for sonar. And then in the 1930s, many ocean-going liners were fitted with these echo ranging devices. So a sound wave is emitted, and you're listening to echoes that are coming back. When the echo hits an object, the signal is returned to the ship, the echo ranging device, and a signal is detected. And in the 1940s, that's when people started to use ultrasound for non-destructive testing in industry, and also the idea for medical diagnosis started to become important. And the first ultrasound devices are called A-mode devices, amplitude mode. So an ultrasound scanner, a transducer, can be made to emit an ultrasound pulse using the piezoelectric effect. So the piezoelectric effect means that certain materials, when they subject to a voltage, a displacement, that they will vibrate, and that generates the ultrasound. But also, the reflected ultrasound signals are detected by the piezoelectric crystal and converted into a voltage signal. So this is a piezoelectric effect. It allows the crystal to act as a transmitter of ultrasound and also as a receiver to detect the signals that are reflected back from different interfaces. So A mode is amplitude mode, and it's basically mapping the amplitude of the echoes that they received back to the transducer, the single crystal. So it's not an imaging, it's just pointing the transducer here on the forehead of the subject and looking into the brain through the skull and detecting the echoes that you can see at the bottom right. So that's amplitude mode. And then people soon realized if you could effectively join the dots, join the signals as a raster scan, a 2D, to produce a 2D image. So if you scan across a plane, then you can build up a 2D image. And these grayscale images are referred to as B mode, brightness mode. So the echo amplitudes are visualized as a grayscale. So if you have a high amplitude signal, that would be represented as a white pixel. And if you have a low amplitude, that would be black. So you have a grayscale image representing the brightness, the amplitude of the echoes that returned. And usually this bears close resemblance to the anatomy. So the early B mode scanners, typically you would have a scanning gantry to move a single element crystal transducer in order to produce that B mode image, the 2D image, along the plane that you're scanning. But people quickly realized that you can develop arrays, an array of transducers. So rather than scanning the transducer and having to build up an image, you could have a large transducer with multiple disc crystals. And this was the first attempt. The problem with such an attempt is you have these large transducers which could be activated in sequence to produce your B mode image, but the resolution is going to be poor because there are too few beams. The beams are large, so the resolution and the sampling of the tissue is going to be poor. A second attempt you could conceive is if you have many narrow transducer piezoelectric elements. If you just excite one element, then you're going to get divergent beams because of diffraction. If the element is very small, then the beam that's emitted out is a spherical beam, a circular wavefront, which is going to give you a poor image. So this is how modern transducers work, essentially. You have maybe 100, 200 elements, and a number of these elements are fired at the same time to produce the beam. By having a number of elements, you're able to produce a collimated parallel beam. And this allows you to produce high resolution images because as you scan across the array, you overlap the whole image plane by moving at the window of the elements step by step. So this allows you to produce an overlapping B mode image, which is of high resolution. And this is how modern linear array transducers actually work. They sweep across the scan plane in order to produce the image. So on the left is a linear array transducer, and on the right is a curvilinear array transducer. Those are the two most common types of modern diagnostic transducers today. So the field that's coming out of these transducers, the beam, effectively, it looks like this. So this is showing a beam from a single crystal, circular element. And there are a few notable features I want to point out because they'll help with your understanding later on. So the beam consists of a near field region, which is close to the transducer, called the Fresnel diffraction zone. And then further away from the transducer on the right is the Fraunhofer diffraction zone, or the far field. And what you might notice is in the near field, if you scan across the beam, you have multiple high amplitude and low amplitude areas. So why is this? What is causing this pattern? And also you have these side lobes. So you have a main beam, and then you have side lobes, which are emitted at an angle to the main beam. And this becomes important for certain artifacts. So there are three concepts that I just want to highlight that would help you explain this kind of beam, these characteristics. Why does it behave like this? The first one is superposition. So you'll be familiar with the idea of superposition. If you have two waves that are in phase, then they will add up in order to give you a high amplitude wave. If the two waves are out of phase, you have destructive interference. So constructive interference or destructive interference depends on the phase of the two waves and how they combine. And if you can imagine any particular point in the field will have different path lengths, and therefore you have different phases, different arrival times of the waves from different points on the transducer. So diffraction is the spherical emission of the wave through a small aperture. And if you consider Huygens principle, each element of the transducer can be considered to be a source of these spherical wavefronts, these circular wavefronts. At any particular point in space, the amplitude of that point will depend on the relative phases of the wavefronts at that point. So these are just three concepts, physics concepts, that will help you explain the beam and why you have a near field and a far field, and why you have these bright and dark zones within the beam. But something to think about later, because it's a lot of information to digest if you've just heard this for the first time. So it's a nice video that puts these concepts, visualizes them, and allows you to appreciate them in a very intuitive way. So hopefully this will play.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
Okay, so that was a nice simulation of some of the concepts that I was explaining earlier. So the key point is that ultrasound scanner sends out a pulse, and then it listens to the echoes that are being received back before moving along the array to create a 2D image. Okay, so how fast does the ultrasound pulse travel through tissue? And what does the speed depend on? The speed at which an ultrasound wave travels is dependent on the medium properties So the speed here is given by the square root of the stiffness divided by the density. So the stiffer the tissue, the faster the ultrasound propagation speed. And the propagation speed is particularly important for ultrasound imaging because the ultrasound scanner is just listening to the time delay between sending out the pulse and receiving the pulse in order to display the position of the target on a 2D image. So it will have to assume a speed of sound at which that pulse is traveling. And the speed of sound that scanners use is 1540 meters per second. That's an average speed of sound through soft tissue. So on the left, you see different tissues like liver, kidney. Fat, you notice fat has a slower speed of sound, 1430 meters per second. Bone is much faster. Because bone is stiffer, it has a faster ultrasound propagation speed. Air, much slower. So for average tissue, 1540 meters per second, the wavelengths are given on the right. So a 10 megahertz ultrasound pulse would have a wavelength of 0.15 millimeters. And these are important numbers to remember because the wavelength of effectively helps determine the resolution of your imaging device. So 0.15 millimeters at 10 megahertz. The speed of sound also has effects in terms of the travel of the beam. So refraction effects. If the ultrasound beam is not perpendicular, an interface between two materials, then you'll get bending of the propagation direction. This is referred to as refraction that you might be familiar with. Snell's law determines the angle at which the beam is bent, depending on the differences in the speed of sound of the two materials. So medium 2, in this example, is the speed of sound is slower than medium 1, and the nice analogy is a car that's traveling a lot of pavement, hits the sand, slows down, and the direction of travel will change, as shown in the middle diagram. So that's refraction, and refraction effects can create many artifacts in ultrasound. Acoustic impedance is another concept that's really key to ultrasound imaging. So acoustic impedance is defined as a response of the particles within the medium in terms of their velocity. So this is not the propagation wave velocity, not the 1540 meters per second wave velocity. This is the actual velocity of the particles as they're vibrating, oscillating due to the pressure wave. So that's the acoustic impedance definition. And that can also be defined in terms of the material density and stiffness as a square root of the density multiplied by the stiffness. The reason why the acoustic impedance is so important is because the acoustic impedance mismatch between materials, between interfaces, that is what determines the amount of ultrasound that's reflected back. So the signal strength that's received by the ultrasound scanner will be dependent on the acoustic impedance mismatch between interfaces. And what you notice in this table is that soft tissue typically has very similar characteristic acoustic impedance. If you look at air, it's much lower. Muscle, bone in particular, is particularly high. So because soft tissue has a similar acoustic impedance, that means the reflection is going to be quite low. So in this equation here, you see that the reflection coefficient is dependent on the difference between the acoustic impedances of the two medium divided by the sum. So this helps explain why ultrasound gel is used. The reflection coefficient will be the acoustic impedance of air minus the acoustic impedance of the muscle divided by the sum. And as you can see, most of the ultrasound signal would be reflected from an air interface, which is why you use gel. Gel has significant water content and therefore will displace the air and allow good transmission of the ultrasound through the body. So that's why gel is used for ultrasound imaging. So other interactions that are important, the ultrasound is propagating through the body. We've already heard how it can be refracted, bent, when you have different speed of sound materials, interfaces. You're going to get different types of reflections. And there are three main types of reflections. One is called specular reflection, when the target, the interface, is much larger than the wavelength. So you can imagine it like a mirror, a smooth interface. This will give you a reflection which can be directed back to the transducer if it's perpendicular to the direction of the wave motion, or if it's at an angle like the middle image shows, then the reflected wave can actually not return to the transducer. It can be reflected into a different direction, in which case the transducer, the ultrasound scanner, will not see that interface because reflection has gone away from the transducer. So that's specular reflection. You also have diffuse reflection when you have a rough surface. When you have a rough surface, the target size is similar to the wavelength, then the ultrasound is reflected in different directions. So that's diffuse reflection. The third type is Rayleigh scattering. And this is when you have very small scattering targets. You have very, very small scattering targets if you're looking at, for example, red cells. If you're doing a Doppler exam, looking at blood flow, then the scatterers are the red cells, which are a few microns in diameter. And remember, a wavelength for 2 megahertz is 0.77 millimeters. So this is much smaller than the wavelength. And in this case, you get weak scattering, and the scattering intensity is proportional to the radius to the power of 6 and the frequency to the power of 4. So these are typical Rayleigh scattering characteristics. Another interaction is absorption, attenuation. So as the ultrasound is propagating through tissue, it will be absorbed, the energy will be converted into heat, mainly. You also have scattering, so the energy is lost, and reflections. The attenuation typically will be represented as an exponential decay, and therefore you can define attenuation coefficients in terms of logarithmic functions. There are two important characteristics between attenuation and the frequency. So high frequency ultrasound will be attenuated more than low frequency ultrasound. So there's always this trade-off between high frequency and high resolution, because high frequency ultrasound will have a small wavelength, therefore you will have a higher resolution image. Because you have more attenuation, you're not going to be able to visualize deep tissues. So the trade-off is between high resolution or high penetration depth. If you want to penetrate deeper into the tissue, say you're looking at a liver, then you want to have a low frequency transducer, but you sacrifice the visual quality, the resolution capabilities of the image. So the last interaction I just want to highlight is nonlinear wave propagation, because this is important for harmonic imaging, which we might talk about later. So if you imagine a sinusoidal wave that's propagating through a weakly attenuating medium, as it propagates, the wave gets distorted, and this distortion might create a shock front. Because the wave is being distorted, you're getting you're generating harmonic content, high frequency signals. The high frequency signals get attenuated more than the low frequency signals, and therefore as the wave is propagated, the high frequency is attenuated more, the amplitude will reduce, and the wave will go back to a sinusoidal wave. The reason why you have this distortion is because the peak refraction, as the wave is compressed, it is effectively stiffer. So the peak positive parts of the wave are traveling faster than the peak negative parts of the wave. So this is causing this distortion of the wave. And if you look at the frequency content of the wave, on the left is if you have a linear pulse, and on the right, you have the nonlinear distorted pulse due to nonlinear propagation. And the frequency content is shown below. If you have a linear pulse, then the frequency content is focused on the fundamental frequency only. And as you have nonlinear distortion, you will get these harmonics generated at multiples of the fundamental frequency. And that's what's used for harmonic imaging. So that's nonlinear wave propagation. And all of these interactions, the way ultrasound propagates through the body, if you can appreciate these basic physics, then it helps you understand and interpret ultrasound images, because many ultrasound images have artifacts. So artifacts are defined as misleading effects in the ultrasound image, anything that's not properly indicative of the structures or motion images, or a spurious signal, which does not represent the physical conditions in the tissue being examined. So there are different definitions of artifacts, and these are just a few. And in order to understand artifacts, you need to understand what are the basic ultrasound imaging assumptions. In order to create an image, you need 3 pieces of information. You need to know the axial distance of the target from the transducer. This is a range, and this is given by the time of arrival. You need to know the lateral position of the target, and that's given by the location, the direction of the beam. And you also need to know the strength, the reflection of the target, which is given by the echo amplitude. So that's 3 pieces of information that you need in order to produce a grayscale image. And the scanner would assume a number of things, that the speed of sound is constant. The scanner assumes 1540 meters per second. It also assumes that the beam axis is straight. It assumes that attenuation is constant, that the pulse only travels to the targets that are on the beam axis, the main beam axis, and then back to the transducer. And also that a thin imaging plane is used. So understanding these assumptions that scanners make will help you interpret different images. So I just want to go through a few artifacts so you can appreciate these. You have a lot of artifacts in ultrasound: reflection type artifacts, attenuation type artifacts, speed of sound type artifacts, side lobe artifacts, beam thickness artifacts, and even speckle can be considered as an artifact. So speckle is that granular appearance that you see in ultrasound images, and that's due to the superposition of the waves that are reflected back from random scatterers. So it's a kind of a random mottled appearance that you get on the image due to these small scatterers. So the first one is a mirror image artifact. Here on the left, you see the true image of the rib, and then below that, you see an artifact image of the rib. This explains how you can interpret a mirror artifact. So I don't know if you can see my mouse, but here on the right, you have a target inside the liver, and you have this white arrow, solid arrow, which indicates the main beam that's producing the image of this target. So if you follow the main beam, it hits the target, and it will display the target over there. If you look on the dashed line, follow the dashed line, it hits the diaphragm, this bright tissue, the liver diaphragm, and then the ultrasound will be reflected from that diaphragm. It will hit the target, the tumor on the right of it, and then it will go back to the diaphragm, hit the diaphragm, and be reflected back to the transducer. But the transducer will only measure the time delay, and it will think that the target is along the dashed line axis. So it will incorrectly position the target as a mirror image along the dashed line. So that's the displayed image of the target. And that's due to this mirror reflection. You can also have reverberation artifacts, and these are quite common. If you have an interface and you get multiple reflections of the ultrasound between the interfaces, again, the scanner just measures the signals and the time delay between received signals, and it will position those signals on the 2D image at increasing depths because of the time delays. So if you see a characteristic equidistant type signals, then that will be characteristic of a reverberation artifact. You can also make use of reverberation artifacts for testing scanners. So when we go to the hospitals and test scanners, we might use a paperclip, as shown here, to look at the reverberation pattern. The paperclip is positioned on the probe. You should only have one reflection, like on the left side, you have the reverberation pattern. On the right, you have two reflective patterns, and this was a fault in the scanner because of the way they were incorrectly wiring the transducer. It was producing double images, and this was detected as a fault during manufacturing of these probes. Shadowing, attenuation type artifacts. If you have a cyst or a liquid will attenuate very weakly, and therefore, as the ultrasound propagates through the liquid, if there's no attenuation, the pulse is going to be larger on the other side, and therefore the higher amplitude pulse will result in larger echoes, and you have an enhancement. So a brighter part of the image behind non-attenuating or weakly attenuated liquids. Or if the target is highly attenuating, such as on the right, you have a solid breast tumor, you will get shadowing because there'll be a loss of signal behind the target. So attenuation type targets are very common as well. And then speed of sound artifacts can result in multiple effects. You can get misregistration of targets, distortion of interfaces, errors in terms of the size of your measurements, and defocusing of the ultrasound beam. So for example, if you have a fat layer between the transducer and the target, because the speed of sound through fat is slower, then the target will be displaced. It will appear deeper than it really is, because the scanner is assuming a speed of sound which is faster than the actual speed of sound. It doesn't know how fast the pulse is traveling through the tissue. It's only measuring the time delay between transmitting a pulse and receiving the echoes back, and displaying that as the distance. So this is highlighting the distortion, the defocusing that you can get if you have interfaces within the path that's resulting in different speeds of sound. Then you'll have the wavefront at the focus will be distorted, and that will reduce the image quality. And then you can have a refraction type artifact. So you get a double image. It looks like a mirror artifact, but it's not. It's actually due to refraction, due to a muscle layer. So the beam is actually being bent, and this bending of the beam is creating a false duplicate image of this aorta in this example. And this explains your refraction artifact. If you have the source, it hits the interface and it's been refracted due to the speed of sound difference. The beam is being refracted, it hits the actual target, the black dot, then it gets returned to the transducer. But the scanner thinks that the target is coming from the direction at which it sent out the beam. So it thinks it has been received by the dotted line, and it's positioning the target at the distance corresponding to that time delay, but along the line that it sent out the beam. So the apparent target position is going to be incorrectly represented due to refraction. And then the last one I want to highlight is side lobes. So the ultrasound beam, as I mentioned, you have the main beam, the high intensity main beam, but in addition to the main beam, you have these weak side lobes, and this can cause artifacts in your images. So in this example, if you look on the right, the yellow arrow on the left image, you have some image that's inside the bladder, which is not a true object. And it's caused by the side lobe, which is coming out of the transducer, striking this bright interface, being returned to the transducer, and the scanner will think it's come from the main lobe, when actually it's come from the side lobe, and therefore will incorrectly position that signal from the side lobe as coming from the main lobe, and the main lobe, the main beam is directed inside the bladder. So it's an incorrect representation of the interface in the bladder. So we covered quite a lot quite quickly, but hopefully some of the basic wave concepts is a bit of revision. We talked about propagation speed, acoustic impedance, specular reflection, diffuse reflection, Rayleigh scattering, refraction, attenuation, interference, diffraction, Huygens principle. We saw how they're important for image formation and to interpret different types of artifacts. So hopefully you found that interesting. If I stop sharing my screen. So thank you for that.
Thank you so much, Dr. Kumar, for that wonderful session. And quickly, for want of time, we just have one question from this session we just completed. How does a medical physicist come into play for ultrasound? Because bulk of our audience are medical physicists or people who are enthusiastic about medical physics. So we'd like to know how we can come in this field. Thank you.
Yeah, so ultrasound is one of these areas which can be quite difficult to get into, partly because of the legislation. It's not like ionizing radiation, where there's a requirement legally to have certain medical physicists in post or people who can do certain types of work. Ultrasound, even in the UK, there's some hospitals that do not have ultrasound physicists. They may not do any ultrasound QA, quality assurance test. So it partly depends on the hospital. There is definitely an increasing awareness of the need for medical physics support to look after ultrasound scanners, to help fix them, maintain them, check them, participate in the procurement, and also introduce new techniques into the clinic. So part of the role of a medical physicist is to help be an interface between researchers and clinical users and help introduce techniques into the clinic. It is, though, a bit of a niche area to get into. There are not that many ultrasound physicists, and especially when hospitals have limited budgets, then the focus inevitably tends to be on ionizing radiation, radiotherapy, those type of modalities. So it's not an easy modality to get into. Yeah, but it's very interesting. A lot of opportunities there.
Okay, thank you so much, Dr. Kumar, for that. Dr. Yubosa's hand is up. Please, can we hear you, ma'am?
I have a question. Yeah, just following Dr. Kumar's thoughts. I'm really concerned. I mean, you have like maybe 30 years or over 30 years experience in ultrasound, and you're still saying that they are not enough. Now, this is the UK that is well established in non-ionizing radiation. So how much more, low and middle income countries like Nigeria? Anyway, my question is two questions actually. When you're talking about the types of artifacts, the mirror artifact, you mentioned that it's a defect from the transducer itself, which would come from the manufacturer. So the simple test you described, which was holding the paper clip to the transducer, is it a test that you do at the point of purchasing the ultrasound machine, or is just one of your routine tests that you do, clinically? Because if it's in my head, I'm thinking it should be at the point of purchasing the machine, so that if you find that artifact, then the machine or the transducer should be returned. Or is it done, or should even be done even before it is supplied to the department? And I think this is a very easy way, segue for medical physicists to get into, ultrasound. You can just easily walk into the clinic and do that simple test and, hold the paper click and say, hey, I think your machine it has a defect. So that's one question. Then the second one is, from your experience, how often do you see these artifacts in clinical practice? Because they are really concerning. If an artifact can change the position of a tumor, then that is of great concern to me as a medical physicist. So how often do you see these artifacts? So two questions in one. Thank you.
Yeah, so if I answer the second one first, these artifacts are very common. The operator needs to be quite skilled in terms of appreciating that what they see on the scanner might not be a true representation of the anatomy. So having some appreciation of how the ultrasound interacts, how it might be reflected if you have a bright boundary, or how it might be refracted and the position might change. They have to build an awareness of these potential problems. So it's not at all uncommon to have these type of artifacts, and it could result in a misdiagnosis, or if somebody is not sure, they would get a more experienced operator to check the images. One big advantage with ultrasound is it's dynamic. So the operator can move the probe in different directions, and this will help establish in their mind if what they're seeing is a true representation of the anatomy or if it's actually misleading them. So just by coming in at a different direction and looking at the anatomy will help visualize and clarify what the true anatomy is, as opposed to what might be caused by an artifact. But definitely artifacts, they're quite fundamental in ultrasound imaging. And some applications like lung ultrasound, which I didn't really mention much, they actually rely on artifacts. So everything that you see and diagnose in terms of lung ultrasound is essentially based on artifacts. So they're making use of the artifacts in order to give the diagnosis and characterize different disease states. So they are a problem, but they can also be used to an advantage in diagnostic ultrasound. Yeah, and the second, the first question. I mean, that was a particularly interesting example. It was actually, hospitals were supplied with these probes, and I think it was medical physicists who first detected that the manufacturers had sold these transducers which had not been wired correctly, and yet you'd imagine they should have been tested properly. They shouldn't really have been issued to hospitals like this. It could have created all kinds of problems. In terms of the question was, do we do the test? Yeah, when we do acceptance testing on scanners, we will use a paperclip test, partly to look for dropout as well. So it's quite common to use a paperclip test to look for elements which are not functioning, because then you won't get the reverberation pattern. That also, in this case, highlighted this double image. You put a paperclip on one side of the probe and you get two images. That immediately would raise concerns in the mind of the person who's doing those tests. But manufacturers don't necessarily do paperclip tests. They wire the transducer. They look at the sensitivity of the crystals, but obviously that error, their tests were not able to pick that up, which highlights the importance of a medical physicist actually in a hospital and picking up issues that manufacturers or commercial providers are not picking up themselves.
Thank you very much.
Thank you very much, Dr. Kumar. Okay, we would be moving on to the next session. At the moment, Dr. Kumar will still be taking us on clinical applications of ultrasound and safety. So if you have more questions, you can just keep dropping them on the chat box, and at the end of the session, we'll take every question. Over to you, Dr. Kumar. Thank you.
Okay, thank you. Oh, that's great. Yes, look at that. Can you see my screen? Can you see the word cloud?
Yes,
Yes,
we
we
can.
can.
Oh, that's great. So thanks. Thank you very much, participants. That's great. You've contributed to this word cloud on ultrasound interaction and artifacts. So that worked quite nicely. I'm going to see if I can move to the next one. And there'll be a second word cloud that you can do based on ultrasound modalities and techniques, which is the topic that I'm going to talk about now. So let me just see how I can I do that? Okay. So yeah, if you could also add to the word cloud regarding different ultrasound modalities that I'm going to talk about and techniques as well. That'd be great. So I'm hoping this is going to be quite an interesting talk, because we're going to build on the introduction, the foundations, and look at clinical examples. And kind of topics I want to talk about: modalities, elastography, harmonic imaging, a little bit about safety and bioeffects, and also therapeutic applications, because it's not so widely appreciated that ultrasound can be used not just for diagnostics, but also therapeutic applications. And I think these are a particularly exciting avenue that can be taken forward in the future. And then a little bit about ultrasound quality assurance and test objects, because this is